All right, I'm going to go ahead and start recording so all my announcements are on here. Okay, number one, and we kind of talked about this right when I was walking in, guys. I need to remind y'all that this is a chemistry lab, and I'm doing this for every class, okay? No eating and drinking in a chemistry lab. I have been rather lenient on that and let that go for lecture, but what has happened, it's my fault because I was lenient and decided to overlook it for lecture. It has trickled over into lab time. And I'll be honest, it's not a single one of y'all in here, but it's some of my Chem 1 students. They're eating. They'll leave their lab station and come to where you're sitting and they'll grab a snack or something. Y'all, I never eat in this room, ever. It's a lab. And those chemicals they're harsh stuff, and they're here, right? Y'all know they're on the lab bench and they're in the environment. So, just a reminder, no eating and drinking. The other thing I have to readdress is cell phones. I always say when we start the semester that I'm going to be, adult about them, but it's getting out of hand. Can y'all multitask?
Yeah.
Did y'all take Miss Jill's psychology class? Because I've talked to Miss Jill about it.
Oh, yeah, I have.
Okay. And I watched a couple of videos this weekend. You can drive down the road and have a conversation in your car. Multitask, right? Driving is something you do every day. But I know, and I think you guys can relate to this maybe, when I'm in a really busy place and trying to pull out, if I have somebody in the car with me and I've been talking, I'll often say, hang on a second. Okay, well, anyway, what I was saying is, have y'all ever, because in that instance, your focus has to be on pulling out in traffic or backing out and not running over somebody with their buggy in the Walmart parking lot, right? And y'all, that's because we recognize a danger there, right? I can't multitask. So what I've noticed is, unfortunately, we are real apt to, if my phone lights up in the middle of lecture, we are real apt to get up and laugh and then come back. And you just lost 15 seconds of what I said. And that 15 seconds is more than 15 seconds because now you have no idea where I'm going next, okay? So I am going to crack down harder on cell phones. I don't want to do that, but I promise you it's for your benefit, okay? That being said, I realize sometimes we need them. We're waiting. A little personal information. Right now, my dad's in the hospital, okay? And I'm hoping he's going to come home. But if I get a text from my mom, I'm going to read it today. And I get that y'all have things like that, okay? And so I understand that. But let me know ahead of time so that I don't say, Hannah, come on. Because I would feel awful if I called her out and then she said, Miss Hurt, my grandma. I would feel awful. So let me know, okay? I'll respect that. But it's hurting your performance, okay? So that's the two things, little soapboxes that I needed to cover with y'all today. So, yes, ma'am, Chloe.
What about like water bottles?
See, and that's the thing. Like I've always thought it's okay to get a drink or a sip of something but the problem is it has trickled over to lab. And, a drink is not that big of a deal to me. I wouldn't want an open drink in here. I get it. So I don't have a good solid answer for you on that. But I'm serious when I tell y'all I never drink in here. I'll go I don't know, there's this invisible barrier between my office door and this room. It stays in my office. I don't bring it in this area. So, okay, lab this week. I sent you guys, and I'm about to walk around the room, so the recording may get a little vague, but I sent you guys an email last Thursday, and what I'm handing you now was attached to that email. Yes? Did y'all look at it? Kinda.
I was hibernating since yesterday. That's what I'm calling it.
So, I seriously thought that some of y'all might show show up today with it already done. That I attached. And Jordan, I kind of thought you might come with it already done. No?
This is right here.
Yeah. I thought he might do it. Did you look at it?
I looked at
I
it.
had no
I didn't even look
certifying
at
at
it.
all last
Okay.
week.
I mean, you're not in trouble. I just thought, I'm sending it to him, like, who's going to go ahead and do it?
I barely
And I thought
actually
you
have done.
Okay. So, I sent it to you in lab. What is your lab going to be this week? It's this. Do y'all remember what I said in that little message? What does it involve? Oh, no. Mm-mm. Excel, yes. It's a graphing lab this week. And so, when we did kinetics, now we're in the equilibrium chapter. But when we did kinetics, I gave you guys 2 formulas. We did this formula. Y'all remember it, right?
Yes.
Okay. Do y'all remember that formula applied if a reaction was first order overall? You remember doing that? Okay. Do you remember anything about what the second order formula looked like? I'm not asking you to know it exactly, but do y'all remember a little bit?
It didn't have the negative K.
It did not have a negative K. Very good.
That's all I know.
Okay.
It was
That's
over-
like the one that
it was
sticks in
under
my mind.
one.
Yeah.
Okay. It was a reciprocal one.
Mm-hmm.
Yeah. Okay. And so these would be, y'all, both of these formulas, when y'all take your test, which is, I have checked the syllabus. Isn't the test next week on chapters 14 and 15?
Don't tell me that.
I think it's Thursday.
I think it's next week. And so I would write these on the board for you. But y'all, like over there, I say this is first order. For the test, y'all need to know that. For the test, you need to know that this one is second order. Okay, you got to keep them straight. I mean, that's always the case, right? You have to know when to use the formula. Also, I reminded you guys that in both cases, these line up with y equals mx plus b. And you have all of these notes in your, well, if you wrote down what I said, and most of y'all do, right? Everybody does. You have this in your background. So let's look at this sheet I just gave you. And it was attached to the message also that I sent last week. So this week's lab is a graphing lab with Excel. I mean, that's what Matthew just said. Remember, I'm going through the little bullets at the top. And I say that, here you go. Remember that for both the plots, the slope of the graph, m, y'all see it? M is equal to the rate constant. And so when it's the first order one, this is what Hannah was saying. The first order graph is going to look like this. The line's going to point down. But the second order graph, it's going to look like that. You're going to submit the graphs and the answers to these questions for a grade. So you have 2 choices on Wednesday of how to submit that. I prefer that you guys come Wednesday with this already finished. And the graphs are printed, and you can write on them, the rate constant is this, the half-life is this, and turn that in. That's what I prefer. If you do not have them finished Wednesday when you come, then you will have to email me, not Canvas message, okay? Email me with the graphs attached to the email. And they will be due by Wednesday at 2:30, because that's when lab finishes. So I'm not going to require that you be in here Wednesday afternoon. If you get it finished, it's just a computer graph. There's no chemicals. Okay? So email or print it and bring it. So let's look at what are you wanting me to email?
I saw on Connect as far as the 2 orders go. What if it's 0 order?
We don't have one of these formulas for 0 order.
Okay, because there was one of those on Connect that I found.
Depends on what it's asking if it's 0 order.
Because it was asking about which way the graph would go.
It asks about the graph for a 0 order?
So one of the last ones, it gave me 3 different ones.
Oh, yeah.
For chapter 14?
It said between 0 order, first order, and second order, which way does the graph go? And it had 2 that were going down, I think one that was going up.
Okay, I didn't do a 0 order one, so it's got to be the one pointing down then. because
I got it right.
first
I was
order
just
points
wondering.
down, second order points up, and if there were 2 pointing down, zero order points down.
I was just wondering because I got it right, but I
Okay.
was just curious because I hadn't heard it through the notes yet.
Okay, yeah, no, and I didn't do that because I wasn't going to do all those, every variation of it. But I'm glad you asked. I'll have to go in and look at it. Okay, problem 1. Look what it says in italics. It says it deals with a gas, and that concentrations of a gas are measured in terms of pressure instead of molarity. So don't let that throw you, y'all. There's no conversion to make. It's just pressure. And I tell you, don't convert to a different unit of pressure. Problem 1 tells you it's first order. Do you guys see where it says from the following data for the first order?
Yes.
Okay, so if it's first order, you know that this is the plot you're doing, the natural log plot. That means what goes on your y-axis. This is where you guys answer. Yeah, the natural log of A. So look in that table. A in that table is the number 502, 335, 180. Are you plotting 502, 335, and 180? Mm-mm.
The log.
You're plotting the natural log of those. So you got to take the natural log of those numbers and enter them in Excel. What is going to go on the x-axis? Time on the x-axis. You don't have to make any adjustment to those numbers. The x-axis is 0, 2,000, 5,000, 8,000, etc. Okay? When you tell Excel to plot those, the natural log of A versus time, it'll give you a straight line. Excel will calculate the slope of that line for you. And so when it says A, determine the rate constant, you get it from the graph. This is important. You do not plug values into this equation and calculate the rate constant. You get the rate constant from the graph. Because it'll give you, you can tell Excel to give me the formula for a line, and Excel will say like y is equal to 1.3 x plus 4. It gives you the line formula. Well, there's the rate constant, 1.3. Okay, so it calculates.
How do you plug it into Excel?
How do you plug it into Excel? In Chem 1, I know not everybody had me for Chem 1, but I did a graphing assignment in Chem 1 to get them used to graphing. Y'all have done graphs in Excel before at some point. I don't know what class. I mean, my kids did it in middle school, used Excel. What else? Anybody had physics? Do y'all graph in physics? Huh? Are y'all graphing? Do y'all use Excel? Okay, so I mean, that's something we have past knowledge of. On Canvas, I have some instructions on how to graph with Excel. So I do have a little tutorial there on Canvas if you want it to help you out. Okay, so A, where do you get the first order rate constant from? You get it from the slope. B, it says calculate the half-life. How are you going to calculate the half-life?
It's T divided by that 0.63.
It's
Okay.
T1.5.
Uh-huh. And you don't have to memorize this, but y'all are just remembering it from maybe using it on Connect or when we went in class. Yeah. You literally take the slope of your graph, plug it in for K, and say 0.693 divided by that K, and that is the half-life. And the half-life, because this data here is in seconds, the half-life will be seconds. It might be 5 seconds or 180 seconds or 2,000 seconds, but you can just leave it as seconds. Okay? So that's problem 1. Problem 2, I don't give you the order of the reaction. But y'all, what do you think? Do you think I'm going to have you do 2 graphs that are natural log graphs?
Nope.
Mm-mm. What might I want in problem 2? Probably a second order reaction, right? So, I mean, there you go. Big hint. Second order reaction. What are you going to plot on the y-axis for a second order?
The reciprocal.
The reciprocal of it. Yes. So you don't plot, like it says the NO2 concentration is 0.1. You don't plot 0.1. You say 1 divided by 0.1. And that's what goes in for your y-axis. What goes on your x-axis? It's still time, right? Because x is time in both graphs. And, I mean, we can see it over here. When I plug in all those numbers, I'll have, what is that? That's 5 data points. I'll have a line going up Excel, you say, hey, give me the formula for the line, and the slope, the slope is the rate constant. On number 2, I say, determine if it's first order or second order. I just told you what it is. I've answered A for you. I told you it's second order. B, I say, determine the rate constant. So you'll pull that from your graph, and you'll say, K is equal to whatever the number is. Do rate constants have units? Yes. Remember, they're funny. They're like m minus 1, s minus 1, or just s minus 1, or whatever. So put your units on it, or it'll cost you a point. That's all there is to the assignment. Some of y'all are masters at Excel. Who's good at Excel?
I can't remember the last time I touched Excel.
I had to learn it for my job, so.
Okay. Yeah, some of us are like, I'm a little worried about Excel. But it's not, once you use it regularly, y'all, I mean, this assignment, it takes no time. I'm talking minutes. I'm talking less than half an hour to do all this. Okay? And graphing with Excel, it really is easy. It's way easier than graphing by hand. Okay? So, there are instructions on Canvas on how to graph with Excel. I will, when I walk out of here today, I'll send you guys a Canvas message, and I'll attach the instructions to it so that you don't have to search for them. Okay? So they'll be in a Canvas message. Now, let's see. We are doing chapter 15. We are talking about equilibrium constants. 678. Could you guys write the equilibrium constant expression for this reaction? Every time I start lecture, I don't know if y'all realize it or not, but I'll take a little step back to what we just did so we can all get back on the same page. So I'm for like 5-10 minutes here, I'm reteaching what I've already told you how to do. Write an equilibrium, bless you, equilibrium constant expression for that. What am I asking y'all to write? I'm asking you to do products over reactants, raise the power of the coefficient. Okay? That's what I'm asking for. K for this is products, the concentration of ammonia, over reactants, raised to the power of the coefficient. So that I just wrote is what I'm asking you guys to write. Is all this coming back to you from last week? K stands for equilibrium constant. A lot of times equilibrium constants are labeled KEQ, stands for equilibrium. Do you recall me mentioning the difference between a KC and a KP?
Pressure.
Yes, KP is pressure, KC is concentration. And so how I have it written for that KC, well, I just realized, y'all, I put a little parentheses at the end of ammonia. I should have put one of these, right? A little square bracket. But do y'all remember me saying square brackets around something mean molar concentration? Okay. A KP for this would look like so. It would say the pressure of ammonia squared divided by the pressure of nitrogen times the pressure of hydrogen cubed. So what I want to point out to you guys, there's not a lot of difference in them. Both of them are products over reactants, raise the power of the coefficient. But if we're using molar concentrations, we typically use square brackets. If we're doing gas pressures, we just put parentheses and put the pressure of everything. How do you know if you're doing a KC or a KP? Well, if you're calculating a KC, the numbers in the problem will be molarity. And if you're calculating a KP, the numbers in the problem might say atmospheres or might say torr. You can convert, KP and KC are not always equal. You can convert between the two using this formula. The KP is equal to the KC times RT raised to the delta N power. Okay? KP and KC are equilibrium constants. KP is for pressure, KC is for concentration. What is R? R. You've seen that before.
Is it the gas constant?
It is. R is still the ideal gas constant. Just to so you guys can impress me, do you remember what that number is?
0.821.
There you go, 0.0821. Liters times atmosphere per mole times Kelvin. Okay, what does T stand for? Temperature. What kind of units does temperature have to be in?
Kelvin.
Has to be in Kelvin. Okay, delta N is new. Kind of, sort of, you guys could figure it out, but what does the little triangle mean?
Change in number.
Change in. Yes, delta, triangle, change in. How do you measure a change in something? You always subtract, don't you? Or difference, however you want to say it. It's the difference. A change in something, isn't the change in always final minus initial? Okay? So that's all that the delta means. What does N stand for? You know this. Moles. N stands for moles. Didn't it stand for moles in PV equals nRT? Okay. So when we're talking about doing the change in moles, what we need to do is take the total moles of gaseous products, because the products is the final, right? Minus the total moles of gaseous reactants, because the reactants are the initial. So it's still final minus initial. It's just products minus reactants, and it's the total moles, because that's what N is. So look at the equation we just did with nitrogen and hydrogen making ammonia. Tell me what the delta N is.
Maybe 4 minus 2.
Other way.
Oh, 2 minus
2 minus 4. Because the total moles of gaseous product, you guys see there's 2 moles of gaseous product. So that's 2. Minus the total moles of gaseous reactant. There's a 1 here. The reactants are 4. So 2 minus 4, the delta N is negative 2. What you think? Okay. Now, I'm about to jump slides, so for the reaction of nitrogen with hydrogen to make ammonia, the Kc is 0.31 at 425 degrees Celsius. Calculate the Kp for the reaction at this temperature. Did I not bring my calculator out here? I so did not. Okay. What you want to do first on that?
Convert Celsius to Kelvin.
Okay, convert Celsius to Kelvin, that's something we're gonna do. I get 698 Kelvin. Now what you wanna do? If we hadn't already, we'd need to calculate the delta N,
Yeah,
but we've got that, we know it's -2. So then, what's kinda, all that's left is put it together, plug it in, yeah. KP is equal to KC Y'all remember that equilibrium constants don't have units. Let's see something. I got 5.18 times 10 to the minus 4. They don't have units.
Okay. I believe I input it in wrong.
I'm not getting that number.
Yeah,
I keep getting like
I get
9.43.
9.43, yeah.
Oh, you know what I did? Y'all are right. I didn't enter 698. I entered 298.
I was so confused.
I was so confused and I kept on
Oh.
trying to
I was
figure
like,
out what
I
I
entered
did.
into 2 different calculators and got the same thing.
Hang on, let me do it right. Oh my goodness, and here I am recording it. That's just peachy. What'd y'all get?
9.4.
That's what I got. Times 10 minus 5.
Yeah.
Okay. I should have 298 instead of 698. Okay. Now.
Moving on to the next one.
Yeah, I'm wondering if I want to do. Okay. Here, it's a lot to write, but that's okay. HF, aqueous, in equilibrium with hydrogen ions, aqueous, and fluoride ions, aqueous. And the Kc for this is 6.8 times 10 to the minus 4. And then H2C2O4, aqueous, yields 2 hydrogen ions,
Oh, you
aqueous.
weren't not kidding about how long it was.
And y'all get there because I'm going to ask you something. Y'all can do this. I'm just doing one out of the book, okay? But y'all, I have another product to write. If I have given you that much, what you see there, then you guys should be able to tell me what goes in that blank. There's only one other thing to write.
CO.
It's not going to be, you're going to have to tell it to me. You're not going to be able to name it.
C2O4.
Yes, C2O4. Agreed? I'm not finished writing it yet.
I was like, I didn't see the other.
You take off the 2 hydrogens It's C2O4. Okay, there's another thing you need on C2O4. It needs to have a -2 charge. Now, before you just like, why, look at it and think about it. Why does it need to have a -2 charge? Yeah, it has swapped over, and like this right here, the H2C2O4 is neutral. If I take the two hydrogens off that are positive, isn't that going to leave it with a -2 charge? See, so, I mean, that, once y'all have done that one, I think you could do anything. The Kc for that is 3.8 times 10 to the -6. Okay. Calculate the Kc for this reaction. C2O4 with a -2 charge, aqueous, plus 2HF, aqueous, yields 2 fluoride ions, aqueous, and H2C2O4, aqueous. We're going to work it together because we have not worked one exactly like this, even though we've worked stuff that's similar enough y'all can do it. Are you guys ready to listen? Y'all know that's why I always pause real long, because we were talking earlier about multitasking. Because I am very much aware that y'all, if you're still writing, you can't listen to what I'm saying with 100%. Yeah, and so, I mean, that's multitask. Okay. Y'all, we did something like this last week, and I'm going to point to the screen, and y'all tell me if you don't remember. I think you'll remember. Last week I said, okay, this, like HF yields H and F, the Kc is 6.8 times 10 to the -4. And then I went in and I changed the equation. And I said, what if I put a 2 in front of HF, a 2 in front of hydrogen, and a 2 in front of fluoride? Remember doing that? And if we double everything, be careful, what do I do to this?
Quadruple. No, double.
Square it.
Ah.
Why? Why do I square it? Because where do the coefficients show up? They're exponents, aren't they? Remember doing that? Okay, so I would have to square this, and that's what would give it to you. Also, we did this. If HF yields H and F, and that's the Kc, what if I took this reaction and I flipped it around?
You do the reciprocal.
You do the reciprocal of this, right? Because then the products of a reactants would be the reciprocal of what they are here. Okay, so what we're about to do is something that you guys learned to do in Chem 1 called Hess's Law.
Oh, Lord.
Okay, but we're doing it with equilibrium constants. So we're going to take this reaction, the HF one, and this reaction, the H2C2O4, which is oxalic acid, so I'm going to call it that instead of H2C2O4, okay? The oxalic acid one. We're going to add these two reactions together, and we want them to look like what I have at the bottom.
What is oxalic acid?
It's an organic acid.
I've never heard of that one.
Okay, do you all see that? When I'm finished, I'm going to write on this and erase so that if you're watching the video, you'll know what I'm pointing at. I want this on the reactant side. That tells me, when I look up here, is it on the reactant side? No, it's on the product side. That tells me I need to flip that equation around. Remember doing this, Hess's Law in Chem 1? So I'm going to take that second equation and I'm going to flip it. I'm going to write C2O4 with a -2 charge and 2 hydrogens in equilibrium with the whole molecule of oxalic acid. And when I rewrite it, y'all, I'm going to leave off the aqueous stuff just for time and for not having to write everything. When I flip it, do I still have the Kc the same number? I've got it, you're right, I have to take the reciprocal of that. So, based on my performance today, somebody's got to check me because I'll punch in the wrong number. 1 divided by 3.8 times 10 to the minus 6 is, I got 2.6 times 10 to the 5. Hannah, did I do it right?
Mm-hmm.
Okay.
Yeah, you did.
Okay? Now, what needs to happen to that top equation?
Same thing.
Doesn't need 6. Or you need to double.
Yes. I don't want to flip it because look where HF is on my final answer. It is on the reactant side. So I need to leave it on the reactant side. But I want HF to have a 2 in front of it. In order to get a 2 in front of it, I have to double the whole thing. What does that do to the equilibrium constant? I square it, don't I? 6.8 times 10 to the minus 4 squared is 4.6 times 10 to the minus 7. Are you checking me? Okay. I know Hannah did the first time.
We got you covered.
Okay, good. Add them together. What cancels out? Well, the two H's cancel, don't they? I mean, that's it. Yeah? And so I'll bring down everything else, the two HS, the oxalate, or the C2O4, the two fluorides, and the oxalic acid. So right now, these two equations add up to look like that I wanted. How do I calculate the KC, the answer? Oh, don't add them. You multiply them together. We did add them in Chem 1 when it was Hess's law, but the math's different here. We got to multiply them together.
What we got together?
We're saying 4.6 times 10 to the minus 7 times 2.6 times 10 to the 5, and I get, well, I got 0.12. Yep. Okay. Okay. Any questions on that? Nope. Good. So we're learning new stuff, but we're really just kind of taking what we already knew and twisting it a little bit. But now we're about to learn really new stuff. Do you guys remember when y'all left last week, I told you we're going to do ice tables? Do y'all remember that? Okay, and that we're going to do ice tables in every chapter for the rest of the semester. And they're really fun. They're really useful. Aren't they fun? Nigel? I don't know. Okay. It's an ice table, and ICE is an acronym. It stands for initial, change, and equilibrium. Okay. I'm going to go to a new slide. This is a new program, so it doesn't scroll. So I'm going to do it over here so I got room. A researcher fills an evacuated 1-liter flask with 0.200 moles of HI. Evacuated. What does that mean?
Clean?
It means more than clean.
It has.
What does evacuated mean? Yeah, it means emptied out. It means there's no air in there. It means it's empty. So it means more than clean. Evacuated means there's nothing in there. Not even oxygen and nitrogen.
How'd they do that?
You pull a vacuum on it. That's what y'all do whenever you vacuum filter. Now we're not getting a total vacuum, but when you hook up a vacuum filter or hook up those vacuum pumps, you're sucking all the air out of those. So it's empty space in there.
I've never heard of evacuated. That was, I was curious.
Yeah. After equilibrium is reached, the concentration of HI is 0.078 molar. Calculate the Kc. Oh, and I'm going to give you a reaction. 2HI gas in equilibrium with hydrogen gas and iodine gas. This is an ice table problem. So we're going to set up a table underneath that says ice. And what goes in an ice table are numbers. Y'all, what goes in an ice table is moles. Do you see that in this problem I told you it's a 1 liter flask? Tell me what molarity means. Molarity means what? Yeah, molarity is moles over liter. So if molarity is moles over liter, and this is a 1 liter flask, then if I put 2 moles in it, 2 moles over 1 liter means it's also I keep saying 0.2. But doesn't that mean it's 0.2 moles? It's also 0.2 molar. It's moles per liter. So if this is 0.078 molar, and it's in a 1 liter flask, doesn't that also mean it's 0.078 moles? Okay. Technically, we're supposed to put moles in this table, but because this is a 1 liter flask, it's going to be consistent. We don't have to worry about making that jump every time. It says the researcher fills a flask with 0.2 moles of HI. From the wording, do you understand that we're starting, our initial amount is 0.200 moles of HI? And so that's how I know from the wording of it to put it on the initial line, and clearly I can tell it's talking about the HI. Are there any questions about why I just wrote 0.2 where I wrote it? Because you guys are going to have to know what to do with the stuff. Okay? Then you tell me, where does the 0.078 go? Okay, it goes to E. How do you know? It says after equilibrium. Goes to E what part? The HI or the H or the I? It's the HI. So I'm going to put 0.078 here. And that means moles, doesn't it? Because it's a 1 liter flask, so it's still moles. Okay, that's all we can put in the ice table. Now, here's a big thing. Did I start out with any hydrogen, H2, or iodine, I2, in this flask? No. Why do I know that? Because it didn't say that I did. Therefore, y'all, the initial amounts of hydrogen and iodine are 0. We talked about this last week, how these are equilibrium reactions. Do y'all remember calculating last week Q's? A Q is a reaction quotient, and we compared the Q to the equilibrium constant, and that told us whether the reaction is moving forwards or backwards. because we've talked about these being dynamic equilibriums. The reactants are to the left of the arrow, the products are to the right of the arrow. Does everybody in here agree with me that I have got to use HI, therefore I'm putting a subtraction mark there, and I have got to make hydrogen and make iodine? It is a simple thing, but you have to understand it. Do you see that there is no possible way I could have negatives on the product side? Because if I'm starting with 0, how can I use what I do not even have? So when you're doing an ice table, it always works out like this, in that one side gets all the positives and the other side gets all the negatives. There's never a mixture of all that stuff going on. Okay? You know what number goes here. How would you come up with what number goes there? I hear stuff. I hear some of the right stuff. Calculate the number that goes there.
I had negative
0.122. Where'd that come from? If I start with 0.2, come on y'all, you know this. If I start with 0.2, what do I have to subtract to get 0.078? I mean, it's 0.2 minus 0.078 is 0.122. That's what I had to use. Okay? So, the change line is really special. Y'all, the change line, and only the change line, follows the stoichiometry. What does that mean? Look at the stoichiometry of the reaction. Do you guys see that the stoichiometry is 2 on HI, 1 on hydrogen, and 1 on iodine? That means the numbers on this change line have to follow that same ratio. So if this number is 0.122, and it is, then what number goes here?
Well, sorry, not negative.
.061. Where does that come from? Because, I mean, when we start the red stuff, this is you guys doing all these calculations. Where did I get .061? Divided by 2. Why did I divide by 2? Do you always divide by 2?
But it's half.
It's half of this, because 2 to 1, you half it. So 0.122, so .061. Okay, what goes here? 0.061, because there's a 1 in front of H2 and a 1 in front of I2. Those numbers there have to be the same. Okay? So, how do I figure out what goes here? Yeah. So what number goes right here? Yep, .061. What number goes right here? 0.061. Oop, I just zoomed in immensely. What does this problem tell me to calculate? The Kc. How do you calculate a Kc? Products over reactants raise the power of the coefficient. Which line do I use to calculate an equilibrium constant?
The end?
The equilibrium line, don't I? So, calculate the Kc. It's going to be 0.061 raised to the first power times 0.061 raised to the first power divided by what? 0.078. Is that also raised to the first power? It's raised to the second power because I got to use the coefficients. So I get 0.61 for an answer.
There's just all the 6 ones and all.
Yeah, there are. The math. What you think? Not bad. That was really, really slow on that one. Let me change slides and give you this next one. The atmospheric oxidation of nitrogen monoxide was studied at 184 degrees Celsius with initial pressures of 1.000 atmosphere NO and 1.000 atmosphere O2. At equilibrium, the partial pressure of oxygen is 0.506 atmospheres. Calculate K. Y'all, I need to put a little subscript on that K. Is it going to be a KC or a KP? It's going to be a KP because I'm doing pressures. And I'm going to give you the equation because when we're doing equilibrium, I always give you the equation. Oops. So that, as I have it written there, that is your problem. That's what you're given on Connect, or that's what you're given on the test. So we're going to do an ice table, and we're going to put the numbers where they go. So y'all do that without me talking you through every number in its placement. Y'all do the ice table. Do y'all have the numbers filled in? Okay. Where does this go? 1.000 atmospheres of NO. Yeah. Do you guys see that that is the initial amount of the NO? Okay? Where does the other 1.00 atmospheres go? Under O2, and it's the initial amount of the O2. Agreed? Because I will not be there to tell you this is what it does, is what it does. Okay, where does the 0.506 go?
On the E line.
On the E line and the O2. So 0.506 atmospheres there. Okay, any questions? What goes here? What goes on the initial line of the NO2? 0. Tell me what's negative. Where do I put my negatives? Because the negatives and the positives goes on the C line.
Negatives are gonna be at the two in O2. Oh no, am I?
Don't you have to have the negatives on the reactant side and the positives on the product side? How do you know that? Because if all you're starting with is reactants, you have got to use those. It's got to move forward. Okay, tell me the next number. Where do I go from here? What do I do? Yes, I'm going to want to subtract the 1 and the 0.506. So when I take the difference in those, what do y'all get? Okay, I'm going to leave off atmospheres on everything because I feel like it's getting too much in there. 0.494. Okay, where do I go now?
Then you go over, it's gonna be the exact same thing.
Okay, so look. It doesn't matter if I get this one first or this one first. It doesn't matter, but do you guys see I need a number in both of those spaces? So, I mean, let's just go left to right. Let's go over here first. What number goes there?
This thing, 0.491.
It's not going to be the same.
It has to be double.
It has to be double 0.494, right? Because the number in front of NO is 2. So what's double 0.494?
That'd be 0.988.
0.988. What number goes over here on the NO2? 0.988. And then what do I do? You just calculate the rest. So 1 minus 0.988 is, what is that, 0.012? And that's 0.988. And then how do I calculate a KP? Plug it in. Remember, you got to raise it to the power of the coefficient. So don't get too happy with just products over reactants, and be sure you raise it to the power of the coefficient. I got 1.3 times 10 to the 4. Did you check that? No? Okay. I got the same thing Hannah got. Surely it's right. Yeah?
Yeah, of course.
Yes. Okay. All right, good. Good. Okay, now, let me ask you this. What if I had a B part to this that said, what's it going to say?
Calculate KC.
Oh my goodness, y'all are so smart. Let's calculate the KC. We got a little formula for that, don't we? I'm going to have to toggle between two slides. Okay, this app does not scroll. So the formula, y'all probably remember it, but it was KP is equal to KC times RT raised to the delta N power. That's the formula. From what I have the KP. KP is 1.3 times 10 to the 4. I'm looking for KC. What's R?
Is automatically
Uh-huh.
0.0821.
0821 liter atmospheres per mole times Kelvin. I'm gonna quit toggling because I know I'm leaving what I'm writing. What is the T?
That,
It's 457.
That's what I got. 457 Kelvin, because I gave you the temperature, 184. Okay, now I'm going to jump back to the slide so that we can all look at the equation together. Talk me through the calculation of the delta N. What's the total gaseous products? 2. What's the total gaseous reactants?
3.
3. What's 2 minus 3? -1. So now solve for KC. Did we get it?
So can you calculate this and just divide it? Or?
You don't divide it by this. You divide the 1.3 times 10 to the 4 by whatever that is. You gotta move that over. Hey, look, when I do this in my calculator, I do 0.0821 times 457, enter, get an answer. Then I raise it to the -1 power, enter, get an answer. Then I do the dividing. Like, I don't punch this whole thing in at one time. I don't try to keep that straight in the air. I work it out.
I always just make it to where KC is equal to whatever.
Right. Some people will go ahead and write this and rearrange it, but it can be a lot to keep track of if it's not a graphing calculator where you can see what you're entering. So,
No, I usually have to write, like, depending if I'm doing it on this one or that one, I have to go back, write it down, and then put it
yeah.
It's kind of like do like on the connects,
Mm-hmm.
if it's multiple steps, and like, if I'm, like, sometimes I do it at work, if we're in downtime or something,
Mm-hmm.
I'll like keep track of my answers by putting the, like, first part in the box, that way I
Right.
can go grab that when I do the second.
Yeah, and that's how we learn to do it. When we're learning order of operation depends on, were y'all really good at math in school?
Yes.
So a lot of y'all probably did order of operation in 7th grade. Is that fair?
Oh,
Because y'all took algebra 1 in 8th grade. Is that, yeah. So when we're learning to do that, we learn. I mean, you're taught to write it down. Just like in elementary, we're taught underline your supporting stuff in your paragraph. Okay. Yes,
Why'd
Chloe.
you multiply it, not divide it?
Multiply what?
Like like when you multiply the 8.0821 times 457.
Uh-huh.
It's raised to the -1, so
-1 means take the reciprocal of that.
yeah, so when it.
But I only take the reciprocal of the RT. So I multiply those out and then I,
1.3x to the 4 divided by.
Uh-huh.
Get there.
mm-hmm.
I get that.
How are you entering times? What did you get? Right here. Right here. What do you have for that? Because I've got 0.02665.
That's what I get.
Oh, are
It
you?
used to be my calculator.
I think it is. You're using that cell phone as a calculator? Whoo, ain't no way I'd do this stuff with a cell phone. Yeah, that's what it is. It's just that annoying calculator.
I make sure it, that's why I always use two, because I, like, say if I get two different ones, I can know which one I did right, which one I did wrong.
Yeah. Yeah, you gotta know how to enter it in your calculator. You gotta understand the order of operation. Okay, that's good for that. That's good for today.
We done for today?
We are done for today.